Look up at the night sky. See those stars? You're standing inside something scientists only discovered in the last decade. Something that's been operating for 13 billion years while we had no idea it was there. For most of human history, we thought galaxies were simple. Collections of stars held together by gravity, floating through empty space. We saw the beautiful spiral arms of the Milky Way and assumed we understood the basic picture. Gas, stars, dust, all swirling around a central point. Nothing more complicated than that. We were wrong, not completely wrong, but missing huge pieces of the puzzle. Between 2013 and 2025, astronomers working independently on different problems kept stumbling across the same strange pattern. Our Milky Way has protective structures. Natural barriers formed by physics that shield different regions of the galaxy from various threats. These aren't force fields from science fiction. They're real physical phenomena created by hot gas, magnetic fields, and the motion of matter through space. The first structure is a massive envelope of superheated gas wrapped around two small galaxies near ours, preventing them from dying when they should have run out of fuel billions of years ago. The second is a containment system around the supermassive black hole at the galaxy's center, trapping radiation that would otherwise flood thousands of light-years of space. The third is a set of patterns at the galactic boundary that reveal how our galaxy interacts with the universe beyond its edges. By the end of this video, you'll understand how each of these structures works, why they matter, and what they tell us about how galaxies function. You'll learn about gas heated to temperatures that would instantly vaporize any planet, about particles moving at 99.99% the speed of light, and about a river of hydrogen stretching across distances so vast that light takes 500,000 years to cross it. We're going to explain all of this using everyday language and simple comparisons. No equations, no technical terms, without clear explanations. Just the story of 3 remarkable discoveries that changed how we understand our cosmic home. Let's start with a mystery that began when astronomers pointed their telescopes at 2 small galaxies next door and found something impossible. In 2013, a team of astronomers using the Hubble Space Telescope was studying the Magellanic Stream, trying to understand where all that stripped gas was coming from. They weren't specifically looking for a protective bubble. They were focused on the stream itself and how it connected to the dwarf galaxies. But their observations hinted at something unexpected in the ultraviolet data. Over the next several years, more teams joined the investigation. They used different telescopes looking at different wavelengths, slowly building a picture of what was happening around the Magellanic Clouds. By 2019 and 2020, multiple studies using X-ray telescopes like Chandra had confirmed what the earlier ultraviolet observations suggested. These are dwarf galaxies. If the Milky Way is the size of a large city, these 2 galaxies are like small towns on the outskirts. You can see them from the southern hemisphere without a telescope. They look like fuzzy patches of light. Ancient sailors used them for navigation across the Pacific Ocean. The Magellanic Clouds are close. Really close by cosmic standards, about 160,000 light-years away for the Large Magellanic Cloud, 200,000 light-years for the small one. That's practically next door when most galaxies are millions or billions of light-years apart, and our Milky Way has been slowly killing them. Here's what happens when a small galaxy gets too close to a large one. Gravity doesn't just pull on solid objects, it pulls on gas too. The bigger galaxy starts stripping away the gas and dust from the smaller galaxy. That gas is the raw material for making new stars. Take away the gas, and the small galaxy becomes a graveyard. All its stars eventually burn out with nothing to replace them. This process has a name: ram pressure stripping. Imagine sticking your hand out of a car window at highway speed. The air rushing past your hand is like the gas in space. Now imagine your hand is made of loose sand. The wind would blow all the sand away. That's ram pressure stripping. The Magellanic Clouds are moving through space at about 400 kilometers per second relative to the Milky Way. That's fast enough to circle Earth 5 times in 1 hour. At that speed, they should be leaving a trail of gas behind them, like a comet leaves a tail. Scientists knew this trail existed. They'd seen it before with radio telescopes. It's called the Magellanic Stream, and we'll talk more about it soon. But something was wrong with the math. The Magellanic Clouds still have gas, lots of it. They're still making new stars right now, today, as you listen to this. The Large Magellanic Cloud is producing about half a sun's worth of new stars every year. That doesn't sound like much, but it means the galaxy is still alive and functioning. According to the calculations, that shouldn't be possible. The ram pressure from moving through our galaxy's outer regions should have stripped away all their gas billions of years ago. These galaxies should be dead husks, dark collections of old red stars with no new stellar nurseries lighting them up. The 2014 team decided to look closer. They used Hubble to study the ultraviolet light coming from the regions between the Magellanic Clouds and the Milky Way. Ultraviolet light gets produced by very specific things in space. One of those things is extremely hot gas. We're not talking about the heat from a fire or even the heat on the surface of the sun. We're talking about gas heated to temperatures above 1 million degrees. What they found made no sense at first. There was a bubble, a massive envelope of superheated gas completely surrounding both Magellanic Clouds. This bubble extended at least 100,000 light-years in every direction from the dwarf galaxies. For scale, the entire Milky Way disk is about 100,000 light-years across. So this bubble around 2 small galaxies was as big as our entire galaxy. The gas in this bubble was heated to between 1 million and 2.5 million degrees. At those temperatures, atoms move so fast they slam into each other hard enough to produce X-rays and ultraviolet light. The bubble was glowing like a neon sign, but in wavelengths human eyes can't detect. And here's the important part. This bubble was protecting the Magellanic Clouds. Think of it like this. You're riding a motorcycle at 500 kilometers per hour through thick fog. That fog represents the outer halo of the Milky Way, filled with gas and dust. At that speed, the fog should rip your helmet off and tear apart anything not bolted down tight. But imagine you have an invisible force field shaped like a teardrop around you. The force field hits the fog first and pushes it aside, creating a smooth path for you to travel through. The fog still tries to get at you, but most of it slides around the shield instead of hitting you directly. That's what the hot bubble does for the Magellanic Clouds. The bubble forms from gas that was already part of the dwarf galaxies. When they started moving through the outer Milky Way region, the ram pressure heated up some of their outer gas layers to extreme temperatures. This created a cushion. The hot gas is less dense than the cooler gas behind it, so it acts like a buffer zone. When the Milky Way's gravity and ram pressure try to rip gas directly from the Magellanic Clouds, they hit this hot bubble first. The hot gas can't be stripped away easily because it's moving too fast. The individual particles in million-degree gas zoom around at thousands of kilometers per second. They're too energetic to be grabbed by the Milky Way's gravity. So the bubble stays intact, wrapped around the dwarf galaxies, taking the punishment that would otherwise destroy them. But here's where it gets complicated. The bubble isn't perfect. It's more like an airbag in a slow-motion car crash. The Magellanic Clouds are still losing gas. The Milky Way is still stripping material away from them. But the bubble slows down the process dramatically. Instead of losing all their gas in a few 100 million years, the dwarf galaxies can survive for several billion years. long enough to keep making stars, long enough to stay alive. When the early teams published their findings around 2013 and 2014, the astronomy community was skeptical. The evidence looked interesting, but it was indirect. They were detecting ultraviolet light and inferring that it came from a hot bubble. They hadn't actually measured the temperature of the gas directly. They hadn't proven the bubble was doing what they claimed. The skeptics said the ultraviolet light could be coming from somewhere else, maybe from young hot stars in the Magellanic Clouds themselves. Maybe from gas that was already part of the Milky Way's halo that just happened to be in that region. The bubble theory was interesting, but not proven. So scientists kept looking. They needed more evidence. The problem with studying something like this hot bubble is that it's invisible to normal telescopes. You can't see it with your eyes or with regular optical telescopes. The gas is too hot and too spread out. It's not like looking at a star or a planet where light is concentrated in one spot. The bubble is enormous and dim, glowing in wavelengths we can't see without special instruments. It's like trying to find a ghost. You need the right equipment to detect it. You need X-ray telescopes, ultraviolet telescopes, instruments that can pick up the faint signature of million-degree gas spread across thousands of light years. And even then, you need to observe for a long time to collect enough light to be sure of what you're seeing. But the strongest confirmation came between 2019 and 2020. Multiple teams used the Chandra X-ray Observatory to study the same region. X-rays get produced by even hotter gas than the stuff that makes ultraviolet light. If the bubble was really there, and really as hot as the first teams claimed, Chandra should be able to see it glowing in X-rays. They found exactly that. The X-ray data confirmed there was gas heated to over 1 million degrees surrounding the Magellanic Clouds. The shape matched predictions. The intensity matched predictions. Scientists started calling it the Magellanic Corona. The bubble was real. By 2020, the evidence was overwhelming enough that most astronomers accepted it. A major paper published that year pulled together observations from multiple telescopes and showed the complete picture. The combined data showed everything. The corona was there, clear and measurable. More importantly, they could see how it was interacting with the gas being stripped from the dwarf galaxies. They could trace the boundary where hot gas met cool gas. They could measure thickness variations in different directions. They could identify places where the corona was failing and allowing more gas to escape. The corona wasn't uniform. It was thicker on the side where the Magellanic Clouds pushed through the Milky Way's halo like the front of a shield absorbing the most impacts. It was thinner on the trailing side where gas leaked out to form that stream scientists had known about for decades. Papers published in 2020 and the years following provided overwhelming evidence. A massive envelope of million-degree gas wrapping around two dwarf galaxies, doing exactly what theory predicted it should do. Slowing the stripping process. Giving the galaxies extra time, this protective layer had been operating for at least 2 billion years. The Magellanic Clouds have been orbiting the Milky Way for a long time. We're not entirely sure when they first arrived, but current estimates suggest they made their first close pass maybe 2 to 3 billion years ago. That's when the bubble would have formed. As soon as they entered the outer regions of our galaxy and started experiencing ram pressure, their gas got compressed and heated, creating this protective layer. And it will keep protecting them for billions of years more. Eventually, the Magellanic Clouds will run out of gas. The bubble helps, but it doesn't completely stop the stripping process. In maybe 5 to 7 billion years, these dwarf galaxies will be dark and dead, having sacrificed all their gas to the Milky Way's gravitational pull. But without the bubble, they would have died 5 billion years ago. They've been living on borrowed time, and the bubble is what bought them that time. There's another fascinating detail about this corona that most people miss. Keeping gas heated to over 1 million degrees for billions of years requires enormous amounts of energy. Where does that energy come from? The answer lies in motion. The Magellanic Clouds are moving fast through the Milky Way's outer regions, and when you move fast through gas, friction creates heat. It's the same principle that makes meteorites burn up in Earth's atmosphere. The dwarf galaxies are essentially creating their own protective layer by moving through an environment that would otherwise destroy them. The corona is powered by the very process that threatens the galaxies. It turns attack into defense. But the physics only works within a specific range of conditions. If the Magellanic Clouds were moving slower, there wouldn't be enough friction to heat the gas to the necessary temperatures. The corona would be cooler and less effective. If they were moving much faster, the ram pressure would overwhelm even a hot corona, and the galaxies would be stripped bare almost immediately. The current speed of 400 kilometers per second sits in what you might call a Goldilocks zone. Fast enough to create a protective layer, slow enough for that layer to actually work. This isn't random chance. The orbital mechanics of satellite galaxies naturally push them toward this kind of balanced state. Galaxies moving too fast get destroyed quickly. Galaxies moving too slow fall into the larger galaxy and merge with it. The ones we observe today, like the Magellanic Clouds, are survivors moving at speeds that allow for long-term stability. Scientists now think this type of corona might be common around dwarf galaxies orbiting larger galaxies. We just couldn't detect them before because the technology wasn't good enough. But if these coronas are widespread, it fundamentally changes our understanding of how small galaxies survive and evolve. Galaxy interactions turn out to be far more nuanced than we thought. The physics that governs matter in space naturally creates these structures. No intelligence designs them. No cosmic engineer builds them. They emerge from basic laws like thermodynamics, gravity, and fluid dynamics operating over vast scales of space and time. The discovery of this corona solved a major puzzle. Before we knew about it, computer models predicted that small galaxies approaching large ones should be stripped of gas almost immediately. Yet we observe many dwarf galaxies still forming stars around the Milky Way and other large galaxies. Some astronomers suggested these dwarf galaxies must be recent arrivals, still in the process of being destroyed. The corona resolves that contradiction. Dwarf galaxies can orbit for billions of years when they have this protective layer. They can survive multiple passages through dense regions of their host galaxy's halo. They can sustain star formation long enough for complex stellar populations to develop. The corona isn't just a physical phenomenon. It's the explanation for why our galactic neighborhood looks the way it does, with multiple small galaxies maintaining active stellar nurseries despite orbiting so close to a much larger galaxy. The Magellanic Stream we're about to discuss is the evidence that this protection is real and has been working for an incredibly long time. It's the proof that you can see with radio telescopes stretching across more than half the sky. If you had eyes that could see radio waves instead of visible light, and you looked up at the night sky from the southern hemisphere, you'd see something spectacular. A glowing ribbon stretching across more than half the sky. A river of hydrogen gas flowing from the Magellanic Clouds back toward the Milky Way, wrapping around our galaxy like a streamer caught in the wind. This is the Magellanic Stream, and it's one of the most important pieces of evidence we have that the hot bubble around the dwarf galaxies actually works. The stream was discovered back in 1974 by astronomers using radio telescopes in Australia. They weren't looking for it. They were mapping hydrogen gas in our galaxy when they noticed something strange. There was a long arc of gas that didn't match any known structure in the Milky Way. It seemed to originate from the direction of the Magellanic Clouds and extended backward along their orbit like a tail. At first, they thought it might be an error. maybe interference from Earth's atmosphere or a problem with the telescope, but the signal was consistent. Every time they pointed the telescope at that region, the stream was there. The discovery was actually somewhat accidental, which is how a lot of astronomy works. The team was using the Parkes radio telescope in New South Wales to survey neutral hydrogen across the southern sky. They were making a map, systematically observing one patch of sky after another. When they looked at the data from the region near the Magellanic Clouds, they expected to see the clouds themselves, which are bright in radio waves because they contain so much hydrogen gas. But there was more, a faint trail extending away from the clouds. At first, it was hard to see because it was so dim compared to the clouds themselves. But when they adjusted the contrast in their images and traced the signal carefully, they realized they were looking at something enormous, a stream of gas stretching across a huge fraction of the southern sky. The team published their findings in 1974, and it caused quite a stir in the astronomy community. Nobody had predicted that dwarf galaxies could leave such obvious trails. It was the first direct evidence that RAM pressure stripping was happening to the Magellanic Clouds, the first proof that our galaxy was slowly consuming its smaller neighbors. Over the next few decades, as radio telescope technology improved, astronomers mapped the stream in more detail. What they found was extraordinary. The stream is massive. It contains about 2 billion times the mass of our Sun in hydrogen gas. That's enough material to build 2 billion new stars. And it stretches across 600,000 light-years of space, making it one of the largest structures associated with our galaxy. Think about that distance for a second. Light travels at 300,000 kilometers per second. At that speed, it would take you 600,000 years to travel from one end of the stream to the other. If you started that journey when the first modern humans were walking around Africa, you'd still have 590,000 years to go. The stream is also relatively narrow compared to its length. In most places, it's about 30,000 light-years wide. So rather than a diffuse cloud, it really does form a distinct ribbon stretched across space. And like a river on Earth, it flows in one direction, following the orbital path of the Magellanic Clouds around the Milky Way. The stream forms because of RAM pressure stripping. As the Magellanic Clouds orbit through the Milky Way's outer halo, gas gets pulled away and left behind. That gas doesn't scatter randomly. It follows the gravitational field of the Milky Way, creating this long arc trailing the dwarf galaxies. Now, here's the key question. If gas has been getting stripped from the Magellanic Clouds for billions of years, creating this enormous stream, why do the dwarf galaxies still have any gas left at all? This is where the hot bubble proves its worth. In 2010, a team of astronomers used the Green Bank telescope in West Virginia to measure the Magellanic Stream in unprecedented detail. They wanted to know exactly how much gas was in the stream and how fast it was being added. Their calculations showed that the stream was growing at a rate of about 1 sun's worth of mass every 10,000 years. That might sound like a lot, but it's actually surprisingly slow. If the Magellanic Clouds were being stripped at the rate you'd expect without any protection, they should be losing gas 10 to 20 times faster. The stream should be much bigger than it is, and the dwarf galaxies should have run out of gas billions of years ago. The fact that the stream exists but isn't enormous tells us something important. The stripping process is happening, but it's being slowed down dramatically. Something is protecting the Magellanic Clouds just enough to keep them alive while still allowing some gas to escape. That something is the hot bubble. The bubble acts like a filter or a brake. It can't stop all the gas from being stripped away, but it reduces the rate by about 80 to 90%. The gas that does escape to form the stream is mostly coming from the outer edges of the dwarf galaxies, where the bubble is weakest. The inner gas, where new stars are being born, stays protected. In 2018, another team used the Australian Square Kilometre Array Pathfinder called ASCAP to make the most detailed map of the Magellanic Stream ever created. ASCAP is an array of 36 radio dishes spread across Western Australia, working together like one giant telescope. The level of detail they achieved was stunning. The ASCAP observations took nearly 2 years to complete. The team had to observe the same regions of sky over and over, slowly building up signal strength until they could see features that were too faint to detect in a single observation. They were looking at hydrogen gas, so spread out that it was barely above the background noise of the universe. It required patience and sophisticated data analysis techniques to pull the stream's structure out of the cosmic static. What made this mapping project particularly challenging was the sheer size of the region they needed to cover. The stream stretches across huge portions of the southern sky. To map it completely, the team had to stitch together hundreds of individual observations, each one covering a small patch of sky. It was like creating a mosaic from hundreds of puzzle pieces, except the pieces were faint radio signals, and the final picture was a 600,000 light-year-long river of gas. They could see structures within the stream, clumps of denser gas, regions where the gas was moving faster or slower, places where the stream appeared to be splitting into multiple substreams. And most importantly, they could measure the age of different parts of the stream based on how far the gas had traveled from the Magellanic Clouds. The oldest parts of the stream, the gas that's traveled the farthest, is about 2 to 2.5 billion years old. That tells us when the Magellanic Clouds first entered the outer regions of the Milky Way and started losing gas. And it confirms that the protective bubble has been operating for at least that long. This dating of the stream is important for another reason. It helps us understand the orbital history of the Magellanic Clouds. For a long time, scientists debated whether these dwarf galaxies were making their first pass around the Milky Way or if they'd been orbiting for much longer. The age of the stream settles that debate. 2 billion years is long enough for several orbits, which means the Magellanic Clouds are not newcomers. They're long-term satellites that have been dancing around our galaxy for eons. This also means the protective bubble has been tested over multiple orbits through different regions of the Milky Way's halo. Sometimes the dwarf galaxies pass through denser regions where ram pressure is stronger. Sometimes through less dense regions where the pressure eases. The bubble has survived all of these different conditions, adapting and maintaining its protective function across billions of years and thousands of light-years of travel. Here's an analogy that might help. Imagine the Amazon River. It's the largest river on Earth by volume, carrying about 200,000 cubic meters of water per second toward the Atlantic Ocean. Now imagine stretching that river across half the solar system. Imagine it flowing not for thousands of kilometers, but for hundreds of thousands of light years. And imagine it flowing continuously for over 2 billion years without running dry. That's what we're looking at with the Magellanic Stream. A cosmic river that's been flowing since before complex life existed on Earth, fed by 2 dwarf galaxies that should have dried up long ago but haven't because they're wrapped in a protective bubble of million-degree gas. The stream also tells us something about the future. As I mentioned earlier, the Magellanic Clouds will eventually run out of gas. When that happens, the stream will stop growing. But the gas already in the stream will continue traveling through space, following the gravitational field of the Milky Way. Eventually, much of that gas will fall back onto our galaxy, where it will be recycled into new stars. So the Magellanic Clouds are essentially donating their star-making material to the Milky Way. It's a slow process, taking billions of years, but it's happening. Our galaxy is being fed by the death of these smaller galaxies. And the hot bubble is controlling the rate of that feeding, making sure it happens slowly enough that the dwarf galaxies can continue making stars for as long as possible. There's something poetic about this process. The Magellanic Clouds are dying, yes, but their death is not meaningless. The atoms that once made up stars in those galaxies will eventually become part of stars in our galaxy. Planets that might form around those future stars will be built from material that spent billions of years in a different galaxy. If life develops on any of those planets, the atoms in their bodies will have traveled an incredible journey across hundreds of thousands of light years, from one galaxy to another. In a very real sense, the Magellanic Clouds will live on through the Milky Way. Their material will be incorporated into our galaxy's structure. Their legacy will be the stars and planets that form from their donated gas. The hot bubble, by slowing down the stripping process, is ensuring that this transfer happens over a timescale long enough for both galaxies to benefit. The Magellanic Clouds get extra time to make stars. The Milky Way gets a slow, steady supply of fresh material that doesn't disrupt its structure. There's a philosophical angle to this that I find fascinating. These dwarf galaxies are dying. There's no way around that. The Milky Way's gravity is too strong, and eventually they'll be consumed, but the bubble gives them time. It allows them to keep creating stars, keep hosting planets, keep allowing the possibility of life to develop on worlds orbiting those stars. The bubble doesn't save them, but it gives them billions of extra years of existence. It's a temporary protection, but on cosmic timescales, even temporary can mean the difference between a galaxy lasting 3 billion years or 7 billion years. That's 4 billion years of additional stars, planets, and possibilities. 4 billion years where, statistically speaking, at least some of those stars probably hosted worlds where something interesting happened. The Magellanic Stream is beautiful when you see it in radio telescope images. It glows in shades of red and orange in false color maps, stretching across the sky like an aurora made of gas instead of light. But what makes it really beautiful is what it represents. It's proof that the universe has built in protection systems, that physics naturally creates shields and buffers that slow down destruction and give cosmic structures more time to exist. Let me give you another way to think about the relationship between the bubble and the stream. The stream is like a scar. It's evidence of an injury that's been happening for billions of years. The Magellanic Clouds are wounded by their interaction with the Milky Way, and the stream is the blood trail showing where they've been. But the wound isn't fatal, not yet. Because the bubble is like a bandage that slows the bleeding enough to keep the patient alive. Without the bubble, the stream would be 10 times larger, the scar would be massive, and the Magellanic Clouds would already be dead, drained of all their gas, nothing but collections of old dying stars. But with the bubble, the wound is manageable. The bleeding is slow. The dwarf galaxies are injured but alive, and they'll stay alive for billions more years. In 2021, scientists made another interesting discovery about the stream. They found that parts of it are being pulled back toward the Milky Way faster than expected. Gravity is tugging on the gas, and in some regions, the stream is starting to fall back onto our galaxy's disk. This infall process has probably been happening for a long time, but we only recently developed instruments sensitive enough to measure it. When that gas falls back onto the Milky Way, it doesn't disappear, it gets recycled. It joins the existing gas in our galaxy and eventually collapses to form new stars. Some of those stars might have planets. Some of those planets might develop life. The atoms that made up the Magellanic Clouds billions of years ago might end up in future civilizations billions of years from now. There's a continuity to all this that most people don't think about. Nothing in the universe is truly isolated. Galaxies interact. Gas flows between them. Stars are born from material that might have originated somewhere else. The Magellanic Stream is one example of this cosmic recycling, and the hot bubble is what regulates the flow rate. The hot bubble around the Magellanic Clouds is the first shield protecting our galactic neighborhood, but it's not the only one. Now we need to journey to the complete opposite end of our galaxy. From the quiet outer suburbs where dwarf galaxies orbit to the chaotic, dangerous center where a monster black hole sits waiting. The center of the Milky Way is 26,000 light-years away from Earth. If you could travel at the speed of light, which nothing with mass can do, it would still take you 26,000 years to get there. Leave Earth today, and you'd arrive around the time humans were painting on cave walls in France. The galactic center is crowded, really crowded. Near the very middle, stars are packed so close together that if you lived on a planet there, you'd see thousands of stars brighter than Venus in your night sky. Some would be so close that if they went supernova, the radiation would sterilize every planet within dozens of light years. And right at the center of all that chaos sits Sagittarius A star. That's the name we gave to the supermassive black hole at the heart of our galaxy. It weighs about 4 million times as much as our Sun, but it's compressed into a region smaller than Mercury's orbit. The gravity near it is so strong that stars orbit at thousands of kilometers per second, completing full orbits in just a few years. By comparison, our Sun takes 230 million years to complete one orbit around the galaxy. Black holes have a reputation for being cosmic vacuum cleaners, sucking up everything around them. But Sagittarius A star is surprisingly quiet. It's not eating much. Most of the gas and dust that falls toward it gets deflected or heated up so much it blows away before crossing the event horizon. The black hole is essentially on a starvation diet. But just because it's not eating doesn't mean it's safe to be near. The region around Sagittarius A star is one of the most dangerous places in the galaxy for a different reason: cosmic rays. Cosmic rays are not actually rays. They're particles, mostly protons, which are the nuclei of hydrogen atoms, but these aren't ordinary protons drifting through space. These are protons accelerated to incredible speeds, sometimes reaching 99.9999% the speed of light. At those speeds, a single proton carries as much kinetic energy as a tennis ball thrown by a professional player. One subatomic particle packs the punch of something you can hold in your hand. When cosmic rays collide with things, they cause damage. Hit a human body, and they punch through DNA, causing mutations. Hit electronic equipment, and they can flip bits in computer memory, triggering malfunctions. Hit a planet's atmosphere in large enough numbers, and they can gradually strip away the ozone layer, exposing the surface to deadly ultraviolet radiation. This isn't just theoretical. We see cosmic rays affecting things right here on Earth. Astronauts on the International Space Station experience higher radiation doses than people on the ground. The atmosphere protects us, but in orbit, they're exposed. Satellites sometimes glitch when cosmic rays strike their electronics. Memory gets corrupted. Instruments malfunction. Engineers design space hardware with extra shielding and error correction specifically to handle cosmic ray impacts. Now scale that up. Imagine if the cosmic ray intensity was 10 times higher or 100 times higher. Satellites would fail constantly. Astronauts couldn't survive in space for more than a few days. Planets without thick atmospheres or strong magnetic fields would be slowly sterilized by constant bombardment. That's what the environment near the galactic center would be like without the cosmic ray containment system. The radiation environment would be hostile to anything without heavy protection. The galactic center produces a lot of cosmic rays. Sagittarius A star creates them when it occasionally eats a little bit of gas. The gas swirls around the black hole in what's called an accretion disk, heating up to millions of degrees before falling in. That heating process accelerates particles to extreme speeds, flinging them away from the black hole like a cosmic particle accelerator. There are also massive stars near the center that explode as supernovas every few thousand years. Each supernova creates a shockwave that accelerates even more particles to near light speed. And the intense magnetic fields in that region bounce cosmic rays around, keeping them trapped and building up their numbers. By all rights, the galactic center should be radiating outward with a flood of these deadly particles. They should be spreading through the galaxy like a wave, bombarding everything in their path. And for a long time, scientists thought that's exactly what was happening. Then in 2021, a team studying data from the Fermi Gamma Ray Space Telescope noticed something odd. They were looking at the cosmic rays in the inner few thousand light-years around Sagittarius A star, and the numbers didn't make sense. There should have been way more cosmic rays spreading out from the center than they were detecting. The cosmic rays were being blocked. Something was stopping them from leaving the galactic center region. At first, the team thought it might be an instrumental error. Maybe their calculations were wrong. Maybe they were misinterpreting the data. But after double-checking everything, they realized the signal was real. There was a containment system around the galactic center preventing cosmic rays from easily escaping. They called it the cosmic ray barrier, and it was completely unexpected. The pattern was clear in the data. Cosmic rays were being produced right near the black hole, but they weren't spreading out the way they should. Most of them were being trapped or deflected by something, unable to flood into the rest of the galaxy. The intensity dropped off much faster with distance than simple diffusion would predict. Scientists came up with three main theories to explain this barrier. And the fascinating thing is, all three theories might be correct. The barrier might not be one thing. It might be a combination of all three working together. First theory, the black hole itself is blowing a wind that pushes cosmic rays back. Even though Sagittarius A star isn't eating much, it's not completely dormant. When gas does fall toward it, some of that gas gets heated so much it blows away before reaching the event horizon. This creates an outflow, a wind of hot gas moving away from the black hole at thousands of kilometers per second. This wind isn't strong enough to blow away stars or even planets, but it can push against cosmic rays. Charged particles like protons interact with gas. When a cosmic ray proton tries to move through this wind, it collides with atoms in the gas and loses energy. It's like trying to run forward into a hurricane. You're technically moving forward, but the wind is slowing you down so much that you barely make any progress. The team calculated that if this wind exists at the right speed and density, it could trap cosmic rays within a few thousand light-years of the black hole. The rays would keep bouncing around in that region, unable to escape, until they eventually lose so much energy they stop being dangerous. Second theory, the magnetic fields near the galactic center are incredibly tangled. Magnetic fields control charged particles. If you've ever played with magnets, you've seen this principle in action. Bring two magnets close together and they either attract or repel depending on which poles you're using. Cosmic rays are charged particles, which means magnetic fields can push and pull on them. The galactic center has strong magnetic fields, really strong. We're talking about field strengths thousands of times more intense than what you'd find in the solar neighborhood where Earth is. These fields get twisted and tangled by the motion of gas clouds, the rotation of the galaxy, and the magnetic field produced by the black hole's accretion disk. Picture a labyrinth made of invisible walls that charged particles can't cross. The cosmic rays try to escape the galactic center, but every time they move, they run into a magnetic field line that deflects them in a different direction. They bounce around like pinballs in an impossibly complex machine, unable to find a clear path out. This theory has strong support because we've actually measured the magnetic field strength near Sagittarius A star. Observations with radio telescopes and infrared telescopes show that the field is strong enough to confine cosmic rays. The physics checks out. But we still don't have a complete map of how those fields are arranged, so we can't say for certain that this is the primary containment mechanism. Third theory, There's a giant ring of gas acting like a physical barrier. About 1,500 light-years from the center, there's a structure called the central molecular zone. It's a dense ring of gas clouds rotating around the galaxy's core. This ring contains millions of solar masses of hydrogen, helium, and heavier elements. It's the raw material for future star formation in the inner galaxy. This ring is dense enough that cosmic rays have a hard time getting through it. When a high-energy particle tries to pass through dense gas, it collides with atoms and loses energy. If the gas is dense enough and the ring is thick enough, most cosmic rays get stopped or deflected before they can break through to the other side. Think of a thick stone wall surrounding a fortress. Arrows can't penetrate it. Attackers have to either go around the walls or find weak points. The central molecular zone might work the same way, blocking cosmic rays from escaping except through specific channels where the gas is thinner. The 2021 paper in Nature Communications described what they called a cosmic ray sea trapped near the galactic center. The particles were being confined by a combination of mechanisms, and the team laid out the evidence for each one. It was a major discovery that explained something astronomers had wondered about for decades. Since then, other teams have continued studying the barrier with different instruments. Ground-based gamma-ray telescopes like HESS in Namibia have mapped the region in even more detail. Observations over the past few years have confirmed that the barrier is real and effective, working on cosmic rays across a wide range of energies. Why does this matter? Because if those cosmic rays escaped freely, they'd make life much harder to sustain in the inner galaxy. Planets within 5,000 to 10,000 light-years of the center would be constantly bombarded by high-energy particles. Any life that evolved there would need to develop protection against constant radiation damage. Complex life, the kind that leads to intelligence, might never get a chance to develop. The cosmic ray barrier gives the inner galaxy a chance. It's not perfect. Some cosmic rays do escape. But the barrier reduces the flood to a trickle, making the inner regions safer than they would otherwise be. Let me give you some perspective on what we're talking about here. The region protected by this barrier covers about 20,000 light-years in diameter. That's a sphere of space containing billions of stars and potentially trillions of planets. Without the barrier, every one of those star systems would be exposed to radiation levels dozens of times higher than what we experience here in the solar neighborhood. Earth sits about 26,000 light-years from the galactic center. We're outside the most dangerous zone, but we're close enough that if the barrier failed, we'd notice. Cosmic ray intensity hitting Earth's atmosphere would increase by about 20 to 30%. That might not sound like much, but over millions of years, it would have effects. More mutations in living organisms, more disruption to the ozone layer, more health risks for any species living on the surface. But for star systems closer to the center, the effects would be catastrophic. A planet sitting 5,000 light-years from Sagittarius A star would experience cosmic ray bombardment 100 times more intense than Earth without the barrier. The atmosphere would be under constant assault. Any magnetic field protecting the planet would be overwhelmed. Surface life would be nearly impossible unless organisms evolved to live deep underground or in the oceans. Imagine living on such a world. Your planet's sky would be constantly lit by auroras as cosmic rays slammed into the upper atmosphere. These wouldn't be the beautiful, occasional auroras we see on Earth. They'd be permanent, intense, covering the entire sky, day and night. The radiation would gradually strip away the atmosphere, layer by layer, until nothing was left but bare rock exposed to space. Any life that managed to exist would need incredible adaptations. Organisms would need redundant DNA repair mechanisms far more sophisticated than anything we see on Earth. They'd need to live under meters of rock or water to shield themselves from the constant particle bombardment. complex surface ecosystems would be impossible. Forests, grasslands, animals walking under open sky, none of that could exist near an unshielded galactic center. The cosmic ray barrier essentially makes the inner 20,000 light-years of the galaxy habitable. Not easy, not ideal, but possible. Without the barrier, that region would be a radiation wasteland where life could only exist in the most extreme, sheltered environments. And here's something most people don't realize. The barrier isn't static. It changes over time in response to what the black hole is doing. When Sagittarius A star goes through an active feeding phase and starts eating more gas, the wind gets stronger. The barrier becomes more effective. When the black hole is quiet, like it is now, the barrier weakens slightly and more cosmic rays leak out. Scientists have found evidence of past feeding events by studying the structure of the gamma-ray bubble around the galactic center. About 6 million years ago, Sagittarius A star apparently ate something large. Maybe a gas cloud, maybe a star that wandered too close. The feeding event created a massive outburst of energy that strengthened the barrier and cleared out cosmic rays from a huge region around the center. The effects of that outburst are still visible today in the form of giant gamma-ray bubbles extending above and below the galactic plane. These are called the Fermi bubbles, discovered in 2010 by the Fermi telescope. They're enormous structures, each one extending 25,000 light-years from the galactic center. And they're evidence that the cosmic ray barrier sometimes becomes so strong, it doesn't just contain the rays, it actively blasts them outward in a directed explosion. The next time Sagittarius A star has a major feeding event, we'll get to watch the barrier strengthen in real time. That might not happen for thousands or millions of years, but when it does, gamma-ray telescopes will capture the whole process. This is the second structure protecting the Milky Way. The first saves dwarf galaxies from being torn apart. The second guards the galactic center and prevents it from flooding the rest of the galaxy with deadly radiation. And as we'll see next, there's a third area at the very edge of our galaxy, where complex patterns are revealing how it interacts with the wider universe. For the past 15 years, scientists operating the Pierre Auger Observatory in Argentina have been collecting data on the most energetic particles in the universe. These ultra-high energy cosmic rays carry so much energy that a single subatomic particle can hit with the force of a baseball thrown at full speed. By studying where these particles come from and how they behave, scientists are learning about the invisible structures at the very edge of the Milky Way. Let me explain what the Pierre Auger Observatory is, because it's not like a normal telescope. It's a cosmic ray detector spread across 3,000 square kilometers of Argentine grassland. That's an area bigger than the entire country of Luxembourg. It uses 1,500 water tanks, each containing 12 tons of pure water, arranged in a grid pattern across this enormous space. When an ultra-high energy cosmic ray hits Earth's atmosphere, it creates a cascade of secondary particles called an air shower. This shower spreads out as it falls, and when the particles hit the water in the tanks, they produce flashes of light that sensors can detect. By analyzing which tanks got hit and in what order, scientists can figure out where the cosmic ray came from and how much energy it had. The observatory has been running since 2008, slowly collecting data on the most energetic particles in the universe. These particles are rare. You might detect 1 per square kilometer per century. So having 3,000 square kilometers of detectors is necessary to catch enough of them to do meaningful science. What makes these observations fascinating is what they reveal about the boundaries of our galaxy. When scientists map where these ultra-high energy cosmic rays come from, they're essentially mapping the edges of cosmic structures. Some particles come from within the Milky Way. Some come from outside, from distant galaxies millions or billions of light-years away. And the boundary between inside and outside matters more than you might think. The Milky Way isn't just a collection of stars floating in empty space with a sharp edge where everything stops. The galaxy fades gradually into intergalactic space. There's a transition region where the density of matter drops, where magnetic fields change their structure, where the environment shifts from galactic to intergalactic. This boundary region has properties we're only beginning to understand. The magnetic field of the Milky Way extends far beyond the visible stars, creating an invisible structure that can affect charged particles. When cosmic rays traveling through intergalactic space encounter this field, they can be deflected, slowed down, or trapped depending on their energy and trajectory. Think of it like trying to push a magnet through a wall of other magnets. The magnetic field at the galactic boundary isn't strong enough to stop everything, but it can redirect particles, especially those at certain energies. This creates patterns in the cosmic ray data that tell us about the structure of the boundary itself. Scientists studying data from Pierre Auger and other cosmic ray observatories around the world have noticed these patterns. The distribution of cosmic rays arriving from different directions isn't random. There are preferences. More particles from some directions, fewer from others. The energy distribution shows features that suggest something is filtering or organizing the incoming particles. But here's the challenge. We don't fully understand what's causing these patterns. There are several possibilities, and scientists are still working to figure out which explanation is correct. First possibility. The magnetic fields at the galactic boundary are stronger or more organized than we thought. We know the Milky Way has a magnetic field. It's complex, with loops and twists and regions where the field suddenly changes direction. Most of this field is weak by laboratory standards, but on cosmic scales, even a weak field can have huge effects when you're dealing with charged particles moving across thousands of light years. At the edge of the galaxy, where gas density drops off and the environment transitions from galactic to intergalactic, the magnetic field might be doing something unexpected. It might be forming a boundary layer where field lines are compressed or aligned in ways that deflect incoming particles more effectively than simple models predict. Measurements of the galactic magnetic field have focused mostly on the inner regions where it's easier to observe. The field strength in the outer galaxy and at the boundary with intergalactic space is much harder to determine. We have rough estimates, but not detailed maps. The field could be stronger at the boundary than current estimates suggest, or arranged in configurations that make it particularly effective at influencing cosmic rays. Second possibility. Dark matter at the galactic edge is somehow affecting cosmic rays. Dark matter is the mysterious substance that makes up about 85% of all matter in the universe. We can't see it directly because it doesn't emit or absorb light. We only know it exists because of its gravitational effects on stars and galaxies. The Milky Way is surrounded by a halo of dark matter extending far beyond the visible stars. We don't fully understand what dark matter is made of. The leading theory is that it's some kind of exotic particle that doesn't interact with normal matter very often. But maybe there are interactions we haven't detected yet. Maybe dark matter does interact with ultra-high energy cosmic rays in ways we haven't discovered. If dark matter particles can scatter or affect cosmic rays, even with a very low probability, the cumulative effect over the vast distances at the galactic edge might be enough to create the patterns we're seeing. The cosmic rays would interact with dark matter particles as they cross the boundary region, and those interactions would leave signatures in the energy and direction distributions we measure. This theory is speculative. We have no direct evidence that dark matter interacts with cosmic rays beyond gravity. But it would explain some of the puzzling features in the data, and it would give us a new way to study dark matter using cosmic ray observations. Third possibility: the transition from galactic to intergalactic environments creates conditions we haven't fully accounted for in our models. The boundary region is complex. Gas density changes, magnetic field structure changes, the intensity of starlight changes. All of these factors can affect how cosmic rays propagate through space. When you have sharp gradients in physical properties, you can get unexpected behaviors. Maybe there are plasma instabilities at the boundary that scatter cosmic rays. Maybe the shock waves from ancient supernova explosions in the outer galaxy have piled up gas and magnetic field at the edge, creating a denser barrier than we'd expect. Maybe the interaction between the Milky Way's magnetic field and the weak intergalactic magnetic field creates interference patterns that affect particle trajectories. These are all active areas of research. Scientists are building more sophisticated computer models of the galactic boundary, trying to predict what effects different configurations of gas, magnetic fields, and radiation would have on cosmic rays. Then they compare those predictions to the actual data from observatories like Pierre Auger. Fourth possibility: we're seeing the combined effects of multiple factors working together. Just like the cosmic ray barrier at the galactic center turned out to be three different mechanisms working in combination, the patterns at the galactic edge might be caused by several effects happening simultaneously. Magnetic fields deflecting some particles, the edge of the dark matter halo affecting others, plasma conditions at the boundary scattering particles in certain energy ranges. The real answer might be a complex mixture of all these factors, each one contributing to the overall pattern we observe. Understanding that mixture requires careful analysis of cosmic ray data collected over many years, combined with theoretical models that can account for multiple physical processes at once. This is frontier science. We're studying the boundary of our home galaxy using the most energetic particles in the universe as probes. Every new cosmic ray detection adds to our understanding. Every improvement in detector technology lets us measure the particles more precisely. Every advance in computer modeling helps us interpret what the patterns mean. Within the next decade, new cosmic ray observatories coming online will give us much better data. The Pierre Auger Observatory is being upgraded with new detectors that can measure not just when and where cosmic rays arrive, but also what type of atomic nucleus created each air shower. This composition data will help distinguish between different theories. New satellite missions are being planned that will detect cosmic rays from space before they hit Earth's atmosphere. Direct detection eliminates uncertainties that come from trying to reconstruct what happened from the debris of air showers. We'll get cleaner measurements of particle energies and directions. And new theoretical work is connecting cosmic ray observations with other kinds of measurements. Radio telescope surveys mapping the magnetic field structure of the outer galaxy. X-ray observations of hot gas at the galactic boundary. Gravity measurements that tell us about the distribution of dark matter. When you combine all these different types of data, you build a complete picture of what the galactic edge is really like. Why does this matter? Because understanding the boundary of the Milky Way tells us fundamental things about how galaxies work. If the edge affects what can enter the galaxy, it influences how galaxies grow and evolve. If magnetic fields at the boundary are stronger or more organized than simple models predict, it changes our understanding of how galactic magnetic fields form and maintain themselves over billions of years. It also matters because the patterns we see might be common to all spiral galaxies. If the Milky Way has distinctive boundary properties, other galaxies probably do too. We just can't study other galaxies' boundaries as easily because they're so far away. The Milky Way is the one galaxy where we can measure these effects in detail because we're inside it. And it matters for understanding cosmic rays themselves. These particles are some of the most energetic objects in the universe. Where they come from, how they propagate through space, what affects their trajectories, these are fundamental questions in astrophysics. The galactic boundary is a natural laboratory for studying these questions. We're living in an exciting time for this research. The technology exists to measure cosmic rays with incredible precision. The theoretical tools exist to model complex boundary conditions. The computing power exists to simulate particle propagation through realistic galactic environments. We're on the verge of understanding something about our galaxy that previous generations of astronomers couldn't even study. The boundary of the Milky Way might not be a dramatic shield in the way the hot bubble or cosmic ray barrier are. It's more subtle, more complex. But it's just as important for understanding what makes our galaxy what it is. The edge defines where the Milky Way ends and the rest of the universe begins. And as we're learning, that boundary has structure and properties that affect everything from the highest energy particles to the large-scale shape of the galaxy itself. This is the third area where the Milky Way's structure creates conditions that matter for the galaxy's evolution and stability. The hot bubble protects satellite galaxies. The cosmic ray barrier contains radiation from the center. And the galactic boundary, with whatever properties it turns out to have, mediates the interaction between our galaxy and the wider cosmos. Let's run through a thought experiment. Imagine all three of these protective structures disappeared tomorrow. The hot corona around the Magellanic Clouds vanishes. The cosmic ray containment at the galactic center collapses. The boundary effects at the galactic edge stop working. What happens next? We'll walk through this scenario carefully because on cosmic timescales, even catastrophes unfold over millions of years, but the effects would be measurable relatively quickly. Start with the Magellanic Clouds. Without the hot corona, ram pressure stripping accelerates dramatically. The dwarf galaxies are moving through the Milky Way's outer halo at 400 kilometers per second. Without any buffer, our galaxy's gravity starts ripping gas away from them at 20 times the current rate. Within the first 10 million years, the large Magellanic Cloud loses 50% of its remaining gas. Star formation drops dramatically. The bright blue regions where massive young stars currently shine start to fade as no new stars are born to replace them. The small Magellanic Cloud, which has less mass to hold onto its gas, fares even worse. It loses 70% of its gas in the same time period. 10 million years might sound like a long time, but in cosmic terms, it's the blink of an eye. It's less than the time it takes our Sun to complete 1/10 of its orbit around the galaxy. From the perspective of the dwarf galaxies, it would be catastrophic. Entire regions of star formation would shut down within just a few million years. The galaxies would visibly darken as the bright young stars burn out and no replacements appear. If there were civilizations in the Magellanic Clouds, they'd watch their night sky change. Stars would disappear. The bright stellar nurseries visible to their astronomers would fade to dark clouds. They'd know something was catastrophically wrong. Their galaxy would be dying in real time, and there would be nothing they could do to stop it. Let's run through a thought experiment. Imagine all three of these protective structures disappeared tomorrow. The hot corona around the Magellanic Clouds vanishes. The cosmic ray containment at the galactic center collapses. The boundary effects at the galactic edge stop working. What happens next? We'll walk through this scenario carefully because on cosmic timescales, even catastrophes unfold over millions of years. But the effects would be measurable relatively quickly. Start with the Magellanic Clouds. Without the hot corona, ram pressure stripping accelerates dramatically. The dwarf galaxies are moving through the Milky Way's outer halo at 400 kilometers per second. Without any buffer, our galaxy's gravity starts ripping gas away from them at 20 times the current rate. Within the first 10 million years, the large Magellanic Cloud loses 50% of its remaining gas. star formation drops dramatically. The bright blue regions where massive young stars currently shine start to fade as no new stars are born to replace them. The small Magellanic Cloud, which has less mass to hold on to its gas, fares even worse. It loses 70% of its gas in the same time period. 10 million years might sound like a long time, but in cosmic terms, it's the blink of an eye. It's less than the time it takes our Sun to complete 1/10 of its orbit around the galaxy. From the perspective of the dwarf galaxies, it would be catastrophic. Entire regions of star formation would shut down within just a few million years. The galaxies would visibly darken as the bright young stars burn out and no replacements appear. If there were civilizations in the Magellanic Clouds, they'd watch their night sky change. Stars would disappear. The bright stellar nurseries visible to their astronomers would fade to dark clouds. They'd know something was catastrophically wrong. Their galaxy would be dying in real time, and there would be nothing they could do to stop it. By 50 million years after the bubble disappears, both dwarf galaxies are functionally dead. They still have stars, billions of them, but those are all old stars that formed before the disaster. No new stellar nurseries. No new planets being born around young stars. No new chances for life to develop in those galaxies. They become cosmic fossils, locked into a slow decline that will last for billions more years. The Magellanic Stream changes too. Instead of growing at a gentle trickle, it becomes a flood. The stream doubles in size within 20 million years as all that stripped gas flows away from the dying dwarf galaxies. Eventually, this extra gas falls back onto the Milky Way and gets incorporated into our galaxy's star formation, but the process is violent and chaotic. Parts of the outer Milky Way experience bursts of star formation as clumps of gas from the stream collapse all at once, creating massive clusters of hot, short-lived stars that quickly go supernova. These supernova bursts aren't harmless. Each one pumps energy back into the surrounding gas, heating it and creating feedback loops that disrupt the normal star formation process. Regions that would have formed stars gradually over billions of years instead burn through their gas in just a few 100 million years, creating brief periods of intense activity followed by long stretches of nothing. The Milky Way's outer disk would look different too. Right now, star formation happens at a steady rate across the disk, with new stars appearing gradually in spiral arms and other dense regions. But with the sudden influx of gas from the dying Magellanic Clouds, you'd get starburst regions, patches of the galaxy where star formation suddenly accelerates by a factor of 10 or more. These starburst regions would be visible from other galaxies as bright blue knots in the Milky Way's spiral arms. They'd be intense but brief, lasting only tens of millions of years before the available gas is exhausted. After the starburst fades, those regions would be left with clusters of massive, hot stars that would live fast and die young, many of them exploding as supernovas within just a few million years of forming. The overall structure of the Milky Way would become more chaotic. The smooth, organized spiral arms we see today would develop irregularities, bright patches here and there where starbursts are happening, dark patches where gas has been exhausted. The galaxy would look less elegant, less symmetric, more like a galaxy that's been through trauma. Now the galactic center. The cosmic ray barrier collapses and suddenly the flood begins. Billions of cosmic rays that were trapped near Sagittarius A star start spreading outward in all directions. The particles move at close to light speed, so the wavefront of deadly radiation expands at 6 trillion miles per year. Within 5,000 years, cosmic ray intensity in the inner 10,000 light-years of the galaxy increases by a factor of 50. Any planets in that region without strong magnetic fields get bombarded with high-energy particles that strip away their atmospheres. Planets with magnetic fields fare better but still experience increased radiation levels that would make life difficult to maintain. Earth is safe. We're 26,000 light-years from the center, and by the time the cosmic ray wave reaches us, it's spread out over such a large volume that the intensity increase is only about 10%. Noticeable if you're a scientist measuring radiation levels, but not enough to cause immediate harm to the biosphere. But the inner galaxy isn't safe. Star systems within a few thousand light-years of the center that might have had a chance of hosting life are now sterilized. The cosmic ray intensity is high enough that even underground life would struggle. Any civilization that managed to develop in that region would need to build extensive radiation shielding or abandon their homeworlds and migrate outward. The cosmic rays also cause secondary effects. When high-energy particles hit interstellar gas, they produce gamma rays. The inner galaxy starts glowing in gamma-ray light, making it one of the brightest gamma-ray sources visible to external galaxies. From the outside, the Milky Way would look sick, like a galaxy with a radiation leak from its core. Astronomers in the Andromeda galaxy, if any exist, would notice the change. They'd see our galaxy suddenly brighten in gamma-ray wavelengths and wonder what catastrophic event just occurred at our center. They might speculate about a supermassive black hole feeding frenzy or a wave of supernovas. They'd be wrong, but they'd know something significant had changed. Now, the edge. The mysterious filter at the galactic boundary stops working and ultra-high energy cosmic rays from intergalactic space pour in. These are the most energetic particles in the universe, carrying so much energy that a single particle could power a light bulb for a second. These particles flood into the outer regions of the galaxy. Unlike the cosmic rays from the galactic center, which are mostly protons, these extragalactic cosmic rays include heavier nuclei, iron nuclei, carbon nuclei, oxygen nuclei, all accelerated to insane speeds by supermassive black holes and colliding neutron stars in distant galaxies. The immediate effect is heating. These particles slam into the outer halo of the Milky Way and dump their energy as heat. The temperature of the gas in the outer halo increases. Not by a huge amount, but enough to change the gas pressure. Higher temperature means higher pressure, and higher pressure means the gas wants to expand. Over the next 100 million years, the outer halo of the galaxy expands outward. The galaxy becomes puffier. Stars in the outer regions spread out as the gas cushion they were embedded in expands. The visible edge of the galaxy, currently sharp and well-defined in images, becomes fuzzy and diffuse. At the same time, some of the gas in the expanding halo reaches escape velocity and leaves the galaxy entirely. The Milky Way starts losing mass. Not a lot, but enough to matter over billions of years. Without that mass, the gravitational pull holding the galaxy together weakens slightly. The rotation curve changes. Stars in the outer regions orbit slower than they used to. Galaxies are dynamic systems held together by a delicate balance between gravity pulling inward and rotation keeping things spread out. Change that balance even slightly, and the entire structure responds. The Milky Way would begin a slow transformation from a tight spiral galaxy to a looser, more open spiral. It would still be recognizable, but astronomers studying it from another galaxy would notice the difference. The spiral arms, those beautiful sweeping structures visible in images of the Milky Way, would start to blur. They'd become less distinct as the density contrast between the arms and the interarm regions decreased. The galaxy would look older, more evolved, like it had aged 1 billion years in just a few 100 million. All three failures combined create a cascade effect. The galaxy loses the Magellanic Clouds as functional satellite galaxies. It develops a radiation problem in the core. It starts puffing up and losing mass from the edges. Over the next billion years, these effects compound. the Milky Way remains a spiral galaxy, but a diminished one. Smaller, less organized, with less star formation and fewer opportunities for planets and life. But here's the thing. This thought experiment isn't going to happen. These structures have been operating for 13 billion years. That's longer than Earth has existed. Longer than the Sun has existed. They're not artificial constructs that can fail. They're natural features of galactic physics, formed by the interplay of gravity, motion, magnetic fields, and the properties of hot gas. The hot corona around the Magellanic Clouds exists because physics requires it. When you move gas fast through other gas, friction heats it up. That's a fundamental principle that doesn't change. As long as the dwarf galaxies keep moving through the Milky Way's halo, the corona will keep existing. The cosmic ray containment at the galactic center exists because of the wind from Sagittarius A's star, the tangled magnetic fields, and the dense gas ring. Those features are stable. The black hole will keep having an accretion disk as long as gas falls toward it. The magnetic fields are generated by the rotation of gas and the motion of the galaxy. The dense ring is held in place by gravity. All of these are permanent features that have existed for billions of years and will continue existing for billions more. The boundary effects at the galactic edge appear to be properties of how galactic and intergalactic environments interact. If they're caused by magnetic fields, those fields are generated by the galaxy's rotation and won't disappear. If they're caused by the dark matter halo, that halo is gravitationally bound to the galaxy and isn't going anywhere. Whatever the mechanism, it's apparently stable enough to have operated for the galaxy's entire lifetime. These shields will keep working long after humans are gone, long after Earth is swallowed by the dying sun in 5 billion years, long after the sun itself burns out and becomes a cold white dwarf in 10 billion years. The shields will still be there, quietly doing their job, protecting the Milky Way and giving it time to evolve at its own pace. That's actually comforting when you think about it. The universe has dangers, cosmic rays, gravitational tides that rip apart small galaxies, radiation from supermassive black holes. But the universe also has protection systems, shields that arise naturally from the laws of physics. And those shields have kept our home galaxy safe for longer than life has existed anywhere in it. The fact that these shields are natural rather than designed makes them more reliable in a way. There's no mechanism that can break, no component that can wear out. As long as the basic physics of the universe continues to work the way it always has, the shields will continue functioning. They're as permanent as gravity or electromagnetism or any other fundamental force. Everything I've told you so far is based on indirect evidence. We've detected ultraviolet light from the hot bubble. We've measured gamma rays from the cosmic ray barrier. We've seen statistical patterns in cosmic ray data that imply a filter at the galactic edge. But we haven't actually seen these shields. We haven't taken pictures of them. We've inferred their existence from the effects they produce. That's about to change. Between 2026 and 2035, multiple space missions and ground-based observatories scheduled to come online will give us the ability to directly image these shields for the first time in human history. We're going to watch them work in real time. Let's start with the hot bubble around the Magellanic Clouds. In 2023, the European Space Agency launched a satellite called XRISM. The name stands for X-ray Imaging and Spectroscopy Mission, though honestly the acronym doesn't matter as much as what it does. It carries an instrument called Resolve, which is the most sensitive X-ray spectrometer ever built. The spectrometers don't just detect X-rays, they measure the exact energy of each photon they detect. Different atoms emit X-rays at specific energies based on their temperature and what's happening to them. By measuring these energies precisely, scientists can determine the temperature, density, and chemical composition of the gas. The satellite will point at the Magellanic Clouds for extended observation periods. Unlike previous X-ray telescopes that could only detect the bubble's presence, XRISM will be able to create detailed maps showing how hot the gas is in different parts of the bubble. It will measure temperature variations down to a precision of 1%. Scientists will be able to see where the bubble is being compressed by ram pressure and where it's thinner and more vulnerable. They'll also be able to measure the composition of the gas. How much hydrogen versus helium versus heavier elements. This composition data tells us where the gas came from. If it matches the composition of the Magellanic Clouds, that confirms the bubble formed from their gas. If it's different, that would be a huge surprise and force us to rethink how the bubble formed. The data from XRISM will let scientists create movies showing how the bubble changes over time. Not actual videos, but sequences of images taken months or years apart that can be played back to show evolution. We'll be able to watch the bubble breathe, expanding and contracting as the Magellanic Clouds move through regions of different gas density in the Milky Way's halo. These time-lapse observations will answer questions we can't currently address. Does the bubble have a stable shape, or does it fluctuate? Are there waves or disturbances that ripple through it? Do parts of it ever break down temporarily and then reform? We'll see all of this directly instead of having to guess from single snapshots. Scientists are particularly excited to observe the boundary between the hot bubble and the cooler gas being stripped from the Magellanic Clouds. This boundary layer is where the physics gets really interesting. It's where million-degree gas meets thousand-degree gas, where the protective shield interacts with the material it's protecting. Understanding how this boundary works will help us understand similar processes happening around other galaxies throughout the universe. In 2029, a proposed mission called the Ultraviolet Explorer might launch if it gets final funding approval. This would be a NASA telescope specifically designed to study ultraviolet light from hot gas in and around galaxies. The Magellanic Bubble is a primary science target. Ultraviolet light comes from slightly cooler gas than X-rays. The bubble has regions of different temperatures, ranging from 1 million degrees where it's hottest down to a few 100,000 degrees at the edges where it mixes with cooler gas. The Ultraviolet Explorer would map those transition zones in detail, showing exactly how the bubble interacts with the surrounding environment. The telescope would create what scientists call a temperature structure map. Think of it like a weather map showing temperature zones, except instead of showing where it's hot or cold on Earth, it shows where the gas is hot or cool in a region of space bigger than our entire galaxy. Scientists could watch how the temperature zones shift as the Magellanic Clouds orbit and interact with different parts of the Milky Way's halo. There's even talk of a really ambitious mission in the 2030s, a probe that would actually fly through the bubble. This would be an interstellar mission, similar in concept to the Voyager probes that left the solar system, except it would be aimed at the Magellanic Clouds. The probe would carry instruments to measure the gas density, temperature, magnetic field strength, and particle composition as it travels through the bubble region. Obviously, this mission is decades away from happening, if it happens at all. The engineering challenges are enormous. The probe would need to travel for thousands of years to reach the Magellanic Clouds. We'd need propulsion technology far beyond what we currently have. And we'd need the probe to remain functional for that entire journey, which means power sources and electronics that can operate for millennia. But the scientific payoff would be incredible. We'd get direct, in situ measurements of the bubble instead of remote observations from Earth. It would be like the difference between looking at the ocean from an airplane versus actually diving into the water and measuring it directly. Now let's talk about the cosmic ray barrier at the galactic center. The next generation of gamma-ray telescopes will revolutionize our understanding of this shield. In 2028, the Cherenkov Telescope Array, called CTA, will be fully operational. This is actually two arrays, one in the northern hemisphere in Spain and one in the southern hemisphere in Chile. Together, they'll have over 100 telescopes all pointing at the same piece of sky, combining their data to create the most detailed gamma-ray maps ever made. Gamma rays get produced when cosmic rays collide with gas. By mapping gamma rays, you can map cosmic rays. The CTA will observe the galactic center for hundreds of hours, building up detailed images showing exactly where cosmic rays are concentrated and where they're being blocked. Scientists expect to see the cosmic ray barrier as a sharp boundary in the gamma-ray maps. Inside the boundary, near Sagittarius A star, gamma-ray intensity will be high. Outside the boundary, it will suddenly drop. By measuring how sharp that transition is and how it varies with gamma-ray energy, scientists can determine which of the three barrier mechanisms, wind, magnetic fields, or dense gas, is most important. The CTA can also watch for changes over time. If the black hole goes through an active period and starts eating more gas, the wind should get stronger and the barrier should change shape. By comparing observations taken years apart, scientists can test whether the barrier is static or dynamic. The sensitivity of CTA is about 10 times better than current gamma-ray telescopes. That means it can detect fainter signals and resolve smaller structures. Scientists will be able to map the cosmic ray distribution around the galactic center with a resolution of a few light-years instead of hundreds of light-years. That's the difference between seeing a blurry blob and seeing actual structure and detail. In 2030, NASA plans to launch the all-sky medium-energy gamma-ray observatory called AMIGO. This is a satellite-based telescope that will map the entire sky in gamma rays at energies current instruments can't easily detect. AMIGO will be particularly good at studying the edges of the cosmic ray barrier, where particle energies are transitional between trapped and escaped. The combination of ground-based telescopes like CTA looking at high-energy gamma rays and satellite telescopes like AMIGO looking at medium-energy gamma rays will give scientists a complete picture of the barrier for the first time. They'll be able to measure its three-dimensional structure, not just its projection on the sky. AMIGO will also be able to watch the entire galactic center continuously, something ground-based telescopes can't do because they're limited by daylight and weather. If Sagittarius A star flares, or if there's a supernova in the central region, AMIGO will capture the event and track how it affects the cosmic ray barrier in real time. Finally, the mysterious filter at the galactic edge. This is the hardest shield to study because it's so far away and so diffuse. But new cosmic ray detectors coming online in the next decade will help. The Pierre Auger Observatory in Argentina is being upgraded right now with additional detectors and better electronics. The upgrade will increase sensitivity to ultra-high energy cosmic rays by about 50% and improve the angular resolution, meaning they can determine more precisely where detected particles came from. The upgrade includes new types of detectors that can measure not just the arrival time of cosmic ray showers, but also their composition. Different types of atomic nuclei create slightly different shower patterns when they hit the atmosphere. By analyzing these patterns, scientists can tell whether an incoming cosmic ray was a proton, a helium nucleus, an iron nucleus, or something else. In 2030, NASA plans to launch the all-sky medium-energy gamma-ray observatory, called AMIGO. This is a satellite-based telescope that will map the entire sky in gamma rays at energies current instruments can't easily detect. AMIGO will be particularly good at studying the edges of the cosmic ray barrier, where particle energies are transitional between trapped and escaped. The combination of ground-based telescopes like CTA, looking at high-energy gamma rays, and satellite telescopes like AMIGO, looking at medium-energy gamma rays, will give scientists a complete picture of the barrier for the first time. They'll be able to measure its three-dimensional structure, not just its projection on the sky. AMIGO will also be able to watch the entire galactic center continuously, something ground-based telescopes can't do because they're limited by daylight and weather. If Sagittarius A star flares, or if there's a supernova in the central region, AMIGO will capture the event and track how it affects the cosmic ray barrier in real time. Finally, the mysterious filter at the galactic edge. This is the hardest shield to study because it's so far away and so diffuse. But new cosmic ray detectors coming online in the next decade will help. The Pierre Auger Observatory in Argentina is being upgraded right now with additional detectors and better electronics. The upgrade will increase sensitivity to ultra-high energy cosmic rays by about 50% and improve the angular resolution, meaning they can determine more precisely where detected particles came from. The upgrade includes new types of detectors that can measure not just the arrival time of cosmic ray showers, but also their composition. Different types of atomic nuclei create slightly different shower patterns when they hit the atmosphere. By analyzing these patterns, scientists can tell whether an incoming cosmic ray was a proton, a helium nucleus, an iron nucleus, or something else. This composition data is crucial for understanding the galactic edge filter. If the filter blocks all particles equally, that suggests one type of mechanism. If it preferentially blocks certain types of nuclei, that suggests a different mechanism. The upgraded Auger Observatory will provide this information for the first time. The composition measurements work by analyzing the way the particle shower develops in the atmosphere. Heavier nuclei create showers that are wider and more spread out. Lighter nuclei create narrower, more concentrated showers. By measuring the distribution of particles hitting the detector array, scientists can work backward to figure out what kind of nucleus started the shower. This is incredibly difficult. You're trying to deduce the properties of a single atomic nucleus from the pattern created by billions of secondary particles after the original nucleus has been completely destroyed in collisions with atmospheric atoms. It's like trying to figure out what kind of bullet hit a wall by studying the pattern of fragments scattered across the room. But the math works, and with enough data, scientists can build up statistical pictures of what's hitting the edge of the galaxy. A new cosmic ray observatory called the Probe of Extreme Multi-Messenger Astrophysics, called POEMR, is proposed for launch in 2031. This would be a satellite mission carrying instruments that can detect air showers from space. Instead of having detectors on the ground like Auger, POEMR would watch from orbit as cosmic rays hit Earth's atmosphere and create cascades of secondary particles. From space, POEMR could observe air showers happening anywhere on Earth, not just where detector arrays are located. This would dramatically increase the number of ultra-high energy cosmic ray events scientists can study. More events means better statistics, which means better measurements of the galactic edge filter. Every atom in your body has a history that spans the galaxy. The hydrogen in your water molecules was formed in the first few minutes after the Big Bang. The carbon in your cells was forged in the hearts of massive stars that lived and died billions of years ago. The iron in your blood was created in supernova explosions that scattered material across thousands of light years. You are not separate from the galaxy, you are made of it. This idea, popularized by Carl Sagan with his phrase, "We are made of star stuff," is literally true. Life on Earth depends on elements that could only be created in stars. Without stars living and dying, without supernovae enriching the interstellar medium, complex chemistry would be impossible. There would be no planets, no oceans, no life. The story of these elements is the story of cosmic evolution. In the beginning, the universe contained only hydrogen, helium, and trace amounts of lithium. These elements formed in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion to occur. But these three elements alone can't make much. They're too simple. To build the periodic table, to create the diversity of atoms needed for planets and life, you need stars. Stars are cosmic furnaces, fusing hydrogen into helium in their cores. But in massive stars, the process doesn't stop there. As the core runs out of hydrogen, it contracts and heats, eventually becoming hot enough to fuse helium into carbon and oxygen. In even more massive stars, this process continues, creating neon, magnesium, silicon, and eventually iron. Iron is the end of the line. Fusing iron requires energy rather than releasing it, so once a star's core fills with iron, fusion stops. The core collapses catastrophically, triggering a supernova explosion that blasts the star's outer layers into space at a significant fraction of the speed of light. In the intense heat of the explosion, elements heavier than iron are created. Gold, uranium, platinum, all forged in seconds and scattered across the galaxy. Remember that invisible skeleton we explored, the interstellar medium threading between the stars? This is how it becomes enriched, how the raw material for future worlds is seeded across light years. Each supernova writes its chemical signature into that cosmic web. Our Sun is at least a third-generation star, possibly more. It formed from a cloud that was already enriched with elements from previous generations. The rocky planets, including Earth, condensed from the leftover material in the protoplanetary disk, building themselves from the ashes of long-dead stars. According to research from institutions like the Carnegie Institution for Science, the solar system contains material from dozens or even hundreds of different stars. Each element has its own history, its own journey through the galaxy, eventually coming together to form the world we inhabit. The calcium in your bones might have come from one supernova, the iron in your blood from another. The carbon that forms the backbone of every organic molecule in your body was forged in a giant star that died before the sun was born. You are a mosaic of stellar deaths, a collection of atoms that have cycled through the galaxy for billions of years, taking different forms, joining different structures, until finally coming together in the pattern that is you. This realization changes the way we think about ourselves. We're not isolated biological machines living on an insignificant rock. We're intrinsic parts of the galaxy's evolution, conscious expressions of cosmic processes that have been operating for 13 billion years. Let me give you some perspective on what we're talking about here. The region protected by this barrier covers about 20,000 light-years in diameter. That's a sphere of space containing billions of stars and potentially trillions of planets. Without the barrier, every one of those star systems would be exposed to radiation levels dozens of times higher than what we experience here in the solar neighborhood. Earth sits about 26,000 light-years from the galactic center. We're outside the most dangerous zone, but we're close enough that if the barrier failed, we'd notice. Cosmic ray intensity hitting Earth's atmosphere would increase by about 20 to 30%. That might not sound like much, but over millions of years, it would have effects. More mutations in living organisms, more disruption to the ozone layer, more health risks for any species living on the surface. But for star systems closer to the center, the effects would be catastrophic. A planet sitting 5,000 light-years from Sagittarius A star would experience cosmic ray bombardment 100 times more intense than Earth without the barrier. The atmosphere would be under constant assault. Any magnetic field protecting the planet would be overwhelmed. Surface life would be nearly impossible unless organisms evolved to live deep underground or in the oceans. Imagine living on such a world, Your planet's sky would be constantly lit by auroras as cosmic rays slammed into the upper atmosphere. These wouldn't be the beautiful, occasional auroras we see on Earth. They'd be permanent, intense, covering the entire sky, day and night. The radiation would gradually strip away the atmosphere, layer by layer, until nothing was left but bare rock exposed to space. Poema would also be able to observe cosmic rays arriving from directions below the horizon, something ground-based detectors can't do. This would give scientists a complete view of the sky and let them study whether the galactic edge filter has directional variations. There's also a proposed mission called the Advanced Particle Astrophysics Telescope, called APT, which would fly a detector into high orbit to directly measure ultra-high energy particles before they hit Earth's atmosphere. This would eliminate the uncertainty that comes from detecting air showers and give us direct measurements of the particles' energies and directions. If APT gets funded and launches around 2033, it could definitively determine whether the galactic edge filter is caused by magnetic fields, dark matter, unknown physics, or something else entirely. Direct detection would give us composition data on the particles, which would constrain the possible mechanisms. Beyond these specific missions, there's a broader trend in astronomy toward multi-messenger observations. Instead of studying objects with just one type of light or just one type of particle, scientists now coordinate observations across many different wavelengths and particle types simultaneously. For the shields protecting the Milky Way, this means combining X-ray data, ultraviolet data, gamma-ray data, radio data, and cosmic ray data all together to build complete models. A group of scientists is already planning coordinated observing campaigns in 2028 and 2030, where multiple telescopes will all observe the Magellanic Bubble, the galactic center, and the galactic edge at the same time. The logistics of coordinating these campaigns are complicated. You need to schedule telescope time on multiple instruments, some on the ground and some in space. You need to make sure all the teams are analyzing their data using compatible methods so the results can be combined meaningfully. You need to plan observations that happen simultaneously, accounting for the fact that some telescopes can only observe certain parts of the sky at certain times of year. But the payoff is worth it. When you observe something with multiple instruments at once, you eliminate uncertainty about whether things changed between observations. You get a true snapshot of the physical conditions at a single moment, which makes it much easier to build accurate models of what's happening. This multi-messenger approach has already revolutionized other areas of astronomy. When scientists detected gravitational waves from colliding neutron stars in 2017, they also observed the event with optical telescopes, X-ray telescopes, radio telescopes, and gamma-ray telescopes. Every telescope saw something different, but together they told the complete story of what happens when two neutron stars merge. The gravitational waves told them about the masses and orbits. The gamma rays revealed the initial explosion. The optical light showed the expanding fireball. The radio waves tracked how the debris interacted with surrounding space. It was one of the most successful coordinated observation campaigns in history, earning a Nobel Prize in 2020. The same approach will work for studying the Milky Way's protective structures. Each type of observation reveals a different aspect of the physics. Combined together, they'll give us the full picture in a way that single wavelength observations never could. Imagine having live feeds from a dozen different telescopes, each showing you a different aspect of these shields. One feed shows X-rays from hot gas, another shows ultraviolet from warm gas. Another shows gamma rays from cosmic ray interactions. Another shows radio waves from magnetic fields. When you combine all those feeds, you can see the complete picture of how the shields work and how they change over time. For the first time in history, we're about to see the invisible. The shields that have been protecting our galaxy for 13 billion years are about to become visible, not to our eyes, but to our instruments. And what we learn from studying them will fundamentally change how we understand galaxies, how they evolve, how they protect themselves, and how they create the conditions that allow stars, planets, and life to exist within them. We'll learn whether other galaxies have similar shields or if the Milky Way is unique. We'll discover if there are more shields we haven't detected yet. We'll find out how these shields change over billions of years as galaxies age and evolve. And we'll understand how the shields interact with each other, whether they're independent systems or parts of a larger integrated defense network. The next decade of astronomy is going to be incredible, not just for studying the Milky Way's shields, but for understanding galaxies in general. We're entering an era where we can watch cosmic structures evolve in real time, where we can test theories with actual observations instead of just mathematical models, where we can see things that previous generations of astronomers could only imagine. And it all starts with these three shields that we barely knew existed 5 years ago. 3 areas of study, one showing how a hot corona wraps around dwarf galaxies, extending their lifetimes by billions of years. One surrounding the supermassive black hole at our galaxy's heart, containing deadly radiation that would otherwise flood the inner regions. One exploring the complex boundary at the very edge of the Milky Way, where cosmic rays reveal patterns that tell us how galaxies interact with the wider universe. We didn't know these structures existed until recently. The hot corona around the Magellanic Clouds was first hinted at in 2013 and confirmed between 2019 and 2020. The cosmic ray containment was discovered in 2021. The patterns at the galactic boundary have been emerging from decades of cosmic ray observations, with new data still being collected and analyzed. But the structures themselves aren't new. They've been operating since the galaxy formed, back when the universe was less than 1 billion years old. They were functioning when the first stars ignited, when the sun condensed from a cloud of gas, when Earth formed and life appeared, when dinosaurs roamed and went extinct, when humans evolved and built civilizations and finally developed telescopes powerful enough to detect the invisible structures that had been there all along. The Milky Way isn't just a random collection of stars, it's an ecosystem. A carefully balanced structure where gravity, motion, magnetic fields, and the properties of gas create natural defense systems. These systems aren't unique to our galaxy. Scientists now think similar shields exist around most spiral galaxies. We just couldn't see them until we developed the right instruments and knew what to look for. What makes these shields remarkable isn't just that they exist, it's that they're self-regulating. The hot bubble maintains itself through the motion that creates it. The cosmic ray barrier rebuilds itself from the very radiation it contains. The galactic edge filter, whatever it turns out to be, appears to be a natural consequence of the boundary between galactic and intergalactic environments. No intelligence designed these shields. No cosmic engineer built them. They arose naturally from physics, which in some ways makes them more impressive. The laws that govern matter and energy spontaneously create protection systems for galaxies. The universe has dangers, but it also has built-in safeguards. When you look up at the night sky, you're looking from inside 3 invisible shields. You're standing on a planet orbiting a star in a galaxy that has been protected for 13 billion years by forces you can't see but that profoundly affect your existence. Without these shields, the galaxy would be a different place, more chaotic, more dangerous, less stable, less suitable for the slow, careful process of star formation, planet formation, and the emergence of life. The next decade of astronomy will transform our understanding of these shields. We'll watch them work in real time. We'll measure their properties directly. We'll learn exactly how they maintain themselves and what limits their effectiveness. We'll discover whether other galaxies have the same shields or different ones. We'll find out if there are more shields we haven't detected yet. But even now, with our limited knowledge, we can appreciate what we've learned. The Milky Way takes care of itself. It has mechanisms built into its structure that protect it from both internal and external threats. It's a galaxy that has survived for 13 billion years not through luck, but through the natural operation of physical laws that create shields, barriers, and filters wherever they're needed. One thing scientists are beginning to realize is that these three shields might not be completely independent. They might interact with each other in ways we don't fully understand yet. For example, the cosmic rays that escape the galactic center barrier have to pass through the outer galaxy to reach the edge. Some of those particles might interact with the hot bubble around the Magellanic Clouds. The bubble might deflect or absorb some of those cosmic rays, providing an additional layer of protection for the dwarf galaxies beyond just shielding them from ram pressure. Similarly, the filter at the galactic edge doesn't just affect particles coming in from outside. It might also trap some particles that are trying to escape from inside the galaxy. The edge filter could be working both ways, keeping external cosmic rays out while also preventing internal cosmic rays from leaving. This would make the galaxy more like a closed system where energy and particles are recycled internally rather than being lost to intergalactic space. These kinds of interactions between the shields suggest that the Milky Way isn't just protected by three separate barriers, it's protected by an integrated defense network where each component affects the others. Change one shield and you change how the others function. It's a system that's more than the sum of its parts. Every star you see in the night sky exists inside this protected zone. Every planet orbiting every one of those stars benefits from these shields. And every potential form of life anywhere in the galaxy, whether it exists now or will exist billions of years from now, owes its chance at existence to forces that have been standing guard since the beginning. The invisible shield protecting the Milky Way isn't one thing. It's three things, probably more. It's a system of systems, each one addressing a different threat, each one operating on principles we're only beginning to understand. And that system has been on duty since before Earth existed. What does this tell us about our place in the universe? It tells us we're not living in a random, chaotic cosmos where anything can happen at any moment. We're living in a structured, organized universe where physical laws create natural protections, where matter and energy arrange themselves in ways that preserve structure rather than destroy it. The shields around the Milky Way aren't special. They're not a gift from a higher power or a lucky accident. They're what happens when physics operates over billions of years in a rotating galaxy with mass and magnetic fields and gas clouds. Similar shields probably exist around millions of other galaxies. We just happen to be born in one of them. But that doesn't make it less meaningful. If anything, it makes it more meaningful. The universe has rules that favor the existence of stable structures like galaxies. Those structures create environments where stars can form and last for billions of years, where planets can orbit those stars without being destroyed, where life can emerge and evolve over unimaginable stretches of time. The shields are part of that story. They're one reason why the Milky Way has been stable enough, safe enough, organized enough to produce a star like our Sun and a planet like Earth. They're one reason why you exist to listen to these words right now. There's a deeper lesson here about the nature of the cosmos. For a long time, humans thought of space as hostile and chaotic. A void filled with dangers like radiation, black holes, asteroid impacts, gamma-ray bursts. And those dangers are real. But what we're learning is that the universe also has structure. It has organizing principles, physical laws that don't just allow for destruction, but also create conditions that preserve and protect. The hot corona around dwarf galaxies isn't protecting those galaxies because the universe cares about them. It exists because friction creates heat, and hot gas behaves in specific ways according to the laws of thermodynamics. The cosmic ray barrier at the galactic center isn't there to make life possible in the inner galaxy. It exists because black hole winds, magnetic fields, and dense gas clouds interact with charged particles in predictable ways. The patterns at the galactic boundary aren't filtering cosmic rays for our benefit. They're the natural result of transitioning from one type of environment to another. But the effect is the same as if these things were designed for protection. That's what makes them so interesting. The universe doesn't need a designer to create structures that preserve and stabilize. The laws of physics do that automatically when conditions are right, and the Milky Way happens to have the right conditions. It will still be on duty billions of years from now, long after we're gone, protecting, filtering, maintaining the delicate balance that makes our galaxy what it is. An island of relative stability in a universe full of violence and chaos. A place where matter can gather, stars can shine, and complexity can emerge from simplicity. That's what the shields mean. They're not just interesting physics, they're the reason our galaxy works, the reason it has lasted so long. The reason it can harbor the kind of stable, long-lived stellar systems where planets like Earth can form and persist for billions of years without being destroyed. You're inside these structures right now. You always have been. They've been operating for 13 billion years, doing what physics requires them to do, creating stable conditions, moderating extreme environments, allowing the galaxy to evolve at its own pace rather than being disrupted by external or internal forces. Think about that the next time you look up at the stars. You're not just looking at distant lights in the darkness, you're looking outward from inside a structured system. A galaxy where natural processes have created conditions stable enough for stars to shine for billions of years, for planets to orbit those stars without being destroyed, and for complexity to emerge from simplicity. The hot corona doesn't care that you exist. The cosmic ray containment isn't watching over you personally. The boundary effects at the galactic edge aren't protecting you by design. But they've created the conditions that made your existence possible. They've kept the galaxy stable and relatively safe for billions of years, giving matter the time and space it needed to organize itself into stars, planets, and eventually, living things that could look up and wonder about their place in the cosmos. And now you know. You know about the corona wrapped around neighboring galaxies, extending their lifetimes. You know about the containment system holding back radiation from the black hole at the galaxy's heart. You know about the complex boundary where our galaxy meets the space between galaxies, where cosmic rays reveal patterns scientists are still working to fully understand.